every year, as you know, one of the Boeing lectures was actually picked by the student. And anyone actually involved in this process, you know, the regular Boeing lecture is some friend's friend, faculty, right? But the student picks, that's a much bigger one. So Qiang was actually picked by student. But somehow they get me to want to introduce him. Anyway, so Qiang actually got his undergraduate from in China, from University of Science and Technology, and then went on to get his PhD at Carnegie Mellon, and then did a postdoc at Chicago. And then he moved a couple of places from Michigan to Hong Kong to Penn State, and now he's at Columbia University. And Columbia has applied math and applied physics too. So he's got as a chair professor there. And Qiang has done a lot of interesting work, so actually I don't really know him that well. So if those guys want me to really say a lot of things about him, I actually don't really know him that well. But check out, so he has done imaging compression, as well as the superconductivity through Ginsburg-Landau equation. And in the last couple of years, he has been working on this non-local diffusion problem. And he has tons of honors. And so the things I particularly try to pick out is in the fellow of SIM and American Mathematical Society, and he elected to the AAS fellow. So we are very glad he's here. And of course, I always want to say, he's willing to come in this special time. So probably we have something special for him. Thank you, Qiang. And let's welcome him.
Thank you so much for coming in this special time. I was joking. I'm not so sure if I'm bringing virus from New York to here or I'm attracting something back. But it's really a great pleasure and honor to be in UW to give this Boeing lecture. I know I have many old friends here. It's a great pleasure meeting them. And also I got to know new friends and also get a chance to meet with very bright students. And particularly honored, as Hong said, that I was picked by the students. It's truly an honor. So I'm going to talk about some work we've been doing recently on non-local modeling. I guess non-local effect, we're seeing that more and more now. Maybe the virus is certainly one sign of that. But there are also lots of connections. There's a non-local connection between UW and Columbia. We actually have faculty graduate from this department. Randy student, Professor Kyle Mandley, he's our assistant professor. We had another Randy student down south, he's our true assistant professor. So it's a strong connection between UW and Columbia. And I was just talking to Professor Tong, and he's good friends with Professor Chu, who is really I should stay close, is really the founding father of the applied math program, Columbia. And by the way, before my lecture, let me advertise that we were expecting to get an RTG grant from ASF for the applied math program. So if there are more students graduating from this program, we're hoping that you can consider to join Columbia in the future, right? Okay, so let me start my lecture. So since I'm talking about non-local model, I'm not so sure how familiar people are to this terminology. So I use this slide to really give a definition or to explain what do I mean by non-local, right? So perhaps we can understand non-local as a relative term in comparison with what is local. An operator is local. You can give a very precise mathematical definition to some degree. Okay, so we can say an operator is local when you operate on a function and the support of the result is always contained in the support of the original function you're operating on. Okay, so it's like you're not going to generate something from nothing. Okay. When f is 0 somewhere in a non-zero measure set, then the action of the local operator always produces 0. Right? So that's in some way is a definition for operator being local. Okay, and then anything non-local we can say that's non-local. Right? There are a couple of classical results you can use to make a better, make this explanation a little bit further. So what kind of operator will share this definition I've given to you? It turns out a very classical result by Peter said that essentially if you want a linear operator to be local, it's going to be limited to be differential operators. Actually, differential operators of finite order. So we're talking about linear differential operator, so it's going to be a polynomial of your first order derivatives, right? So that means local operators actually are very limited. On the other hand, if you borrow from function analysis, any linear operator, you can have this kernel representation. This is called Schwarz kernel theorem. You can view this like your race representation theorem, things like that. So if you want to describe any linear operator, basically you just need to define this kernel function k, and tells you, how the information and x and y are related to each other. Okay. If you combine the two results together, then this almost says that essentially a local operator will be an operator with a kernel that has a support concentrated on the diagonal, so it's only when x equal to y, and given in the form of a direct delta function where it's basically its derivatives, its finite number of derivatives. And that's the limitation of what local operator can do. Then any other kernels you can think of, make this well-defined operator, will give you a non-local operator. In particular, this will mean operators that can have support or have built-in interactions off diagonal. So when x is not at the position y, and they still interact with each other or affect each other, right? So we've actually tried to do a little bit more discussion along this line in a recent paper with Bjorn Enquist and my former student Xiaochuan Tian and UT Austin. But non-local operator is really not new from a historical perspective. Okay? There have been a lot of discussions, both in mathematics and maybe in physics. A lot of well-known names like Rayleigh, Van der Waals, or Korteweg, and they talked about the importance of accounting for non-local interactions to describe our physical world. A special case of non-local operators are given by what's called fractional operators. So actually in mathematics, there's a surge of interest in fractional equations for fractional derivatives. So that traces back all the way to the fathers of calculus, to Leibniz and Riemann and those people. So this also has a long tradition in mathematics. Okay. Just to maybe, because I'm at UW, so I would say maybe there is some local connections to non-local modeling. I read a paper of Bernard and Nathan some years ago. So they were working on some models of Bose-Einstein condensation. So some 15 years ago, I was also interested in studying quantized vortices in BEC system. So I borrowed this quote from the paper. I didn't read very carefully the mathematics part, but this quotation strikes me. So they said that in almost all applications where the nonlinear Schrodinger equation is relevant, right? It actually is a outcome of a simplification from a non-local description, right? So they give examples: water waves, plasma physics, nonlinear optics, and BECs, and so on. Okay. So actually, in some of the works by Landau, there were similar remarks of this. Okay. So I just want to use this to say, maybe non-local interactions or non-local models are much more generic than we thought. Okay. So maybe the goal of my lecture today is try to advocate non-local model as something perhaps more general than local models. And you can think, you can understand this in terms of their physical origin, so where they come from, or mathematical origin. They can play roles to say as alternatives to local models, or serve as bridges between different models, as well as new mathematical tools to understanding existing local models. So if time permits, I will try to illustrate that using different examples. Okay. So non-local models have been around for a while, but I'd like to draw your attention to a new area of non-local modeling, which is maybe what most of my lectures are about, and it's something that I've been working on in more recent years. It's on system of equations. Most of the mathematical physical equations are dealing with vector fields and tensor field, whether it's solid mechanics or fluid mechanics. So in those problems, the physical quantity of interest are represented by vectors. Working on non-local systems are much more challenging and also interesting than just working on scalar models of non-local nature. And so this adds more complexity into the consideration. That's one special feature. The other special feature of the system we work on is non-local models, but non-local models with a finite range of interactions. So this range is now 0, but it does not extend to infinity. It's characterized often by what we call as a horizon parameter or radius of interaction. We just use delta. So this characterizes what would be the range of interaction. Right? So we confine the range of interaction, or you can just say in terms of the kernel function, the support of the kernel will be concentrated near a band of width delta away from the diagonal x equal to y. Okay? So introducing this finite range provided a number of features. One is that you can think about the limit when this range of non-local interaction goes to 0. So non-local interaction become localized. Okay? And if your kernel also gets localized along the diagonal as you shrink the non-local range of interaction, you just end up with a local operator. And so this local operator could be a differential operator. So you can say in this way, maybe you can recover many local PD models from a non-local model by shrinking the range of interactions. So that's one connection you can make. I can give you a couple of examples. So here I give you two formulas. It's maybe the first one will be the way you can think about is for function of u of interest. You can think about taking a finite difference with some length scale s. So this takes a finite difference. But rather than doing a discrete difference operator on a single scale s, I actually average over a continuum scales and weight it with some kind of a kernel function or density function. Right? So you can think about this omega delta as maybe a Gaussian for simplicity. Right? And delta could be the variance or symbolizes the support. And as the variance, as the support goes to 0, this becomes a delta function. And then that difference operator just goes to the limit when s goes to 0, and that gives you the first order derivative. Right? So a non-local operator like this will have a local derivative as its limit. And you can also take your second order difference and weight it in a certain way and localize to give a second order differential operator if the quantity of interest, the function u, is smooth enough to allow you to take derivatives. Right? So at least that gives you an idea. Yeah, there are lots of non-local operators. They can provide interesting connections or special cases to the familiar differential operators. But at the same time, you can imagine to have a non-local interaction kernel where the range of interactions goes to infinity. And if you pick the kernel to be somehow scaled inversely proportional to the distance of x minus y to a certain power, and actually you can relate that to a fractional differential operator given in a integral form. Right? So the infinite limit of a non-local operator can recover fractional operators. And they're certainly more general if you pick other non-power like fractional kernels. Right? At the same time, I do computational work. So computers often deal with discrete quantities. So when you have an integral operator, you can just think about that as an idealization of really a discrete, for example, Riemann sum, and only when the number of summation terms goes to infinity, then that becomes an integral. Or if you do numerical quadrature, you discretize the integral operator, it just becomes a discrete set of sums. Right? And that kind of operator can represent a graph operator or operator defined on networks. Hong was just showing me in his office about, if you think about Markov transition process and your transition operator, and that can be also viewed as a discretized version of a non-local operator, right? Because these kernels basically can describe the interactions or transition probabilities between particles I and particles J's. It doesn't matter whether I and J are adjacent or not. Okay. So in a way, again, it's just the same message I was saying. Non-local models could be more general depending on the choices of non-local kernels, and possibly they would link many different models together. And another feature is that if you have quantities of interest, a function f, which may not be differentiable, may not be able to take derivative in the classical sense, and you can always integrate, or it's easier, or it probably make better sense to integrate rather than differentiate. Right? So if you're modeling, if you want to find the effective model on a certain length scale to capture singularities of the underlying process, maybe integral equations can tolerate more singular solutions than their classical local counterpart. All right. The reason that we got interested in studying this particular class of non-local models, that models with finite range of interaction, certainly, as an applied mathematician, is driven by applications, particular applications for mechanics. As I said, mechanics, often you're dealing with vector quantities or tensors, so that's why you need to think about system equations. So the motivation comes from fractures, Parry dynamics. This is a non-local model proposed some years ago. And then there's also connections to a very popular methods in computational fluids, like this thing called smooth particle hydrodynamics. That has non-local features I will try to explain. I'm also affiliated with the Data Science Institute in Columbia to study high-dimensional geometry of data. And I often think, you can think of that in a discrete setting, or you can think about using PDEs, but it's probably also quite natural to think about as the complexity of data gets more and more, and maybe think about this continuum setting or continuum limit in terms of non-local models. Okay. In addition, studying systems and also with a finite range of interaction can offer you much richer mathematical structures. Going from a single variable calculus to multivariable calculus, you learn much more about the geometry, right? So it's Gauss theorem, divergence theorem, all of that are dealing with multivariable quantities. Okay. Because there's less work on this particular topic, and one of the things that also motivated us is perhaps we can try to study this problem from a more fundamental level. See if we can have a new framework, just like for the PDEs, we have the classical calculus, we have the classical calculus variation, and now if we switch to an integral equation, can we do things on a non-local setting? Okay, so set up the fundamental building blocks. Okay, so I would say it's really a nice area of to work on. One is that it's closely tied to applications, and also it can enrich you to the mathematical side. You can develop elegant theories, and then with non-locality, the computation becomes much more challenging. And of course, lots of times the application was geared towards finding singularities in solutions and also processes with anomalous behaviors, and so which are harder to do computationally, and that challenge is also make us motivated. Okay. So I certainly won't have time to go into a lot of details, but let me just do a little bit advertising. Hopefully nothing to be alarmed about. If students interested in learning this more, we just published a monograph with SIAM based on the lectures I gave a couple of years ago on the Conference Board of Mathematical Sciences under the same title. Okay. And there's electronic versions available. You can easily download. All right. So let me begin by giving you some application examples first to say how non-local models indeed, or where do they arise, or how are they used. The first example I picked is what motivated me to study. It relates to the so-called models of continuum mechanics or fractal mechanics. Okay, that there was work by physicists trying to rewrite continuum mechanics given in the form of PDEs as non-local models, right? So this Parry dynamics was proposed by a physicist at Sandia National Lab, Stuart Schilling, some almost 20 years ago. And he recently won, 5 years ago, maybe won the USACM Bedichico Prize, honor for his contribution to this area for inventing or for initiating research on Parry dynamics. So Parry dynamics is, has a lot of, as a new theory, has a lot of, generated a lot of debates and controversies, but I think people are appreciating what it can do now. Right? His central idea is rather than the classical Newton's law, F equal to ma, where you write down the forces as derivatives of your displacement field, instead you write this as an integral. So you don't have the, the spatial derivatives anymore, but instead they were replaced by some non-local integrals involving the displacement field. Right? And now his idea is to apply this to study fractures and cracks, and then you have a discontinuous deformation field U, and therefore if you're not differentiating and you're only doing integration, maybe you'll have a better chance of not running into any inconsistency on the modeling level. Right? So it turns out that they were using this to do a lot of fancy simulations with fracture patterns when a projectile hitting a target. Sandia's weapons lab, I guess. So they were able to do a lot of simulations that are much more difficult to do by traditional means. Right? So this was simulations based on Parry dynamics, and that was a much simpler two-dimensional simulation done by my student, just to try to validate this experiment that when you pour the edges of a material, then you may have a crack pass, and then at some point it'll bifurcate. And we make sure that when the material constant is given correctly, you can reproduce, classical result or results you get from experiments. So all in all, this has been developed into a sort of a new technology in this area. And the key thing is that this non-local paradigmic model allows you to treat discontinuous displacement more effectively, and then you can use that to make better material failure predictions. Right? And at least that was the objective of this. So this was one example that motivated us, where really the non-local model becomes now an alternative. Right? But let me also give you another example where we think that non-local model can also provide a bridge between different models. This is on anomalous diffusion. Okay. So earlier on, I provided a sort of a example of a non-local derivative. So in some sense, if you localize this, you get standard derivative. We use t as the independent variable, so you say this is time derivative. So on one hand, we have the familiar equation, heat equation or diffusion equation. This is for normal diffusion. So typically, you get mean square distance that grows in time linearly. And this appears very often in nature. Okay. But there are also processes that was considered as, for example, subdiffusion. So the mean square distance goes to increases with time sublinearly, like a fractional power and other things. Right? And this fractional derivative will be a non-local derivative with an infinite horizon, right? So you can say it accounts for the history, but history all the way from the starting point. Okay? Rather than have a finite history, you have history as long as you need. Okay? So we studied a model in between of them. So we are no longer using the local derivative nor the global fractional derivative. Instead, we use a non-local derivative, but only with a finite history. So the particles only remember where they were, but up to a period of delta, size delta. Okay? So you may be curious what kind of process this can govern, or what can this be used for? Well, it turns out that in many recent experiments, biological or chemical experiments, there are lots of observation that there is crossover between different diffusion regimes. You could have a process where this process starts to be subdiffusion, so the mean square distance travels much slower than time, but later on it transitions into a normal diffusion regime and start to pick up. Right? So in fact, those were experimental pictures showing you a subdiffusion and later on into a linear diffusion. So this is in a log slope, so you become linear, and similarly with this should be in the standard scale, and you have sublinear and then go into linear. Right? And if you simulate actually the model we call nonlocal in time dynamics with a finite memory, so what happens is that if you pick your kernel to be something like a fractional power early on, then indeed it's producing a subdiffusive behavior later on. But as time goes on, then you start to become a normal diffusion. Actually, over a long time, this will be modeling a normal diffusion. So the single model will be capturing the two-stage process and it will give you the seamless transition between the two different stages. So on one hand, when delta goes to 0, you have a limit of normal one, but then as delta goes to infinity, you are going to reach your fractional one. And so you can think about what happens to this is that maybe a simple explanation is to say, well, you only have finite memory when the process started initially. The finite memory accounts for a big portion of the whole history, right? So really, you have very strong memory. What happens when you're young? You remember 2 years. Well, maybe 2 years old. That's all the lifetime. But when you're getting old, so later of the stages, well, that finite memory compared to the whole history is become less and less significant. So you're becoming less and almost like memory-less, right? So relatively speaking, the memory relative roles played by memory become insignificant, and then that almost become more like Markovian, and then you start getting into the normal diffusion regime. Right? So that will be the intuitive explanation, and that really is what the mathematics is telling you. Right? So in this regards, you can have a nonlocal model with a finite interaction range or with a finite history to model to link two different models together as a bridge. And you can also use this in some sense to model equation with delay. Right? That's another bridging role that you can use nonlocal models for. Okay? The next example I want to give you, so we have a nonlocal model that captured the crossover between different regimes, and because of the bridging roles. The third example I also want to give you is want to talk about the roles played by nonlocal models as a tool to understand or approximate the local models. So you may have a PDE, a local model. This is well accepted. There's nothing wrong, okay? But you may want to say somehow by doing a non-localization, you can find better understanding of the local model. The example I want to choose is the so-called smooth particle hydrodynamics, okay, or SPH by short. This actually had a much longer history. It was originally proposed by some astrophysicists in the 1970s. It's quite popular with many citations. Okay. It was proposed as a kind of a numerical method to discretize your PDEs, or maybe MHD or fluid mechanics equations. Okay. But the way you discretize the PDE is not like you do finite difference. You have a PDE, just rewrite your operator as a finite difference stencil. What they do is typically a SPH approximation involving a two-step process. The first step, you actually try to write a spatial derivative, for example, a spatial gradient. You actually put that as a non-local integral average. And they call this as a non-local smoothing, right? Because doing integrals is like smooth the differentiation operator. You start to do non-local averaging now, right? So then once you get into an integral form, then you can do a numerical quadrature to write this as a sum over some particles. And so that's your second step of numerical discretization. HPH community always talk about the end product. So the PDE, let's say your Navier-Stokes equation, now end up to be a discrete interaction among particles. But except that in this process, there was a regularization or non-localization involving some range of interactions of delta. So if the particles are within a delta distance scale, they interact, but away from delta range, they don't interact. Okay, so that's what HPH is. A lot of people like it. That's why it's so popular. But also a lot of people hate them. Right? So you almost have a dichotomy. Either they love it or they hate it. Okay. The reason is that people use this very nicely. Find that this is very easy for complicated geometry problem. You don't have to do any meshing. You can deal with complex geometry, and it's a particle-based method. The code is easy to write. Okay, you just follow where particles are, then that's it. But the people who don't like them say that it's very easy to, the code will break down very easily. If you change your parameter slightly, before it was working and suddenly it doesn't work anymore. Right? So it's not very robust. Right? And there are lots of mysteries surrounding this. For example, you're trying to regularize maybe a Laplacian, a standard second-order derivative. But when you build in this HPH literature, standard Laplacian will be a composition of divergence and gradient. That's what we learned in calculus. But in the HPH, they will advertise, they say, don't treat this as a HPH divergence composed with HPH gradient. This is not a good way to do it, because this is very sensitive to the so-called particle disorder. If particles move in a peculiar way, some particles get clustered, some regions are just particle, then HPH will break down, right? So you develop methodology, but you say that, well, you have to be careful. You cannot do what you think normally you would do. Right? So that was mystery to us. We're wondering what's going on. Okay. So it turns out that the cruising, we think one of the crucial missing pieces in this is that people have not paid much attention to the process of when you rewrite your local model on the continuum level, replace that by a non-local model, whether the non-local continuum model is a good one or not. Okay. It turns out that if you can rewrite a local model as a approximate that by a better non-local model on the continuum level, then you discretize, then you could avoid issues like this. You can provide much more robust and stable discretizations. Okay. So in this way, this non-local diffusion model was not believed as the true physics. The local model is. But it serves as a tool to understand why a numerical method to a local model works or not, or works in a robust way or not. Okay, so that's another role of non-local models. Okay. So maybe I talked too much about this application side. As I said, we try to develop this theory in a more systematic way. We're a little bit ambitious, so we said that PDEs was based on vector calculus. We have beautiful theorems, divergence theorem, Gauss theorem, and so forth. And is there a non-local analog? Right? So there's something you can say, and so we wrote a paper about this. But this area actually remains to be much more developed, especially when we're thinking about capturing more geometry, intrinsic natures. It's probably better to develop this from a differential geometry point of view. So maybe develop a non-local exterior vector calculus. So talking about non-local forms rather than non-local operators. But that work is still ongoing, and there are a lot of interesting to work on over there, right? But let me just summarize a number of things so we were able to do. So once you have a calculus sort of setup, then you can try to do calculus variation to understand the various kind of problems that relates to mechanics or relates to physics. Okay? So you would have to develop your machinery from function analysis. So that's one of the area we spend a lot of time to work on. Okay, to talk about variational problems and all the necessary functional tools, and allows you to study those variational problems. That's in one direction. Okay, and then to link this mathematical development back to the application again. Okay, so for example, for Parry dynamics, before we get into the area, there's very little known about the mathematical properties of that complicated non-local integral equations. And now we can say whether those equations make sense or not mathematically because of this background. Basically, we studied all the linear Parry dynamics models, so that's almost complete. We started some simpler cases of nonlinear models. Right? And then in particular, we studied models that can be used to study, for example, crack propagation in certain specialized materials with simplified constitutive laws. Okay? And in the process of doing this kind of mathematical analysis, the work was able to provide some useful guidance to practitioners. Right? So I'll give you a couple of examples. One of them is we realized that some of the non-local models proposed in the Parry dynamic community was not suitable mathematically. So they have some kind of intrinsic instabilities. This was somewhat discovered in practice when people do simulations, but they do not know whether it's due to numerics or it's due to the modeling aspect, and we can provide a better understanding, right? And we also understood now why this so-called SPH Laplacian cannot be obtained as a composition of SPH divergence and SPH gradient because of that, again, instability issues. So this resolved a mystery. Okay. We also discussed some numerical discretization of Parry dynamic models and showed that, in fact, there were popular methods used by engineers that may provide you incompatible discretizations with the classical elasticity models. This is really a serious problem because if you have a new code developed to capture some complex physical process like crack propagation, but if this code cannot even produce simple results with, say, linear elasticity when there's no crack and things like that, people tend to lose faith in what you're doing, right? So you want to avoid things like this. Okay? So maybe let me use spend a little bit of time to talk about this discretization issues, right? So we summarize this as a term we called as developing numerical discretizations, which are so-called asymptotically compatible. If you're a SIME member, you may get your latest SIME review. We had a paper as a SIME Digest article. It was a republication of a paper we published 5-6 years ago with my former student, Xiaochuan Tian. So she's really a brilliant student. It's always a pleasure to work with a good student like that. Her first paper, 2013, was also on similar subject. Got a SIME Outstanding Paper Prize, and then she went on to complete the thesis. That won her a Best Dissertation Prize from the from Association of Women Mathematicians. So the thesis really summarized, in some sense, this whole machinery of asymptotically compatible numerical schemes, right? So let me try to explain what we're doing here. We're trying to develop numerical methods to solve a non-local counting models that's characterized by a modeling parameter delta, which measures the range of non-local interactions. So on the continuum level, right, I have a non-local model which has a physical parameter delta, measures the non-local interaction. So the model was parameterized by this delta, but there's no discretization. So I use H as a discretization parameter, so H equal to 0. There's no discretization. I'm interested in develop numerical methods to discretize that by introducing some discretization, or this could be inversely proportional to the number of particles. Right, so as the numerical resolution level gets better and better as the number of particles increases, I'm hoping my numerical methods will produce the solutions on the continuum level. Right? That's the goal we do. But at the same time, I also want my method to be robust in the sense that I know for some simplified non-local models, when it gets localized, they should recover some nicely behaved nonlinear continuum PDE models, okay, local models. So I know that path. So the question is whether I can reproduce this limit on the numerical level to preserve that same limit, right? If you have a numerical methods that allows you to recover the non-local model for finite horizon, but also a local model when the horizon parameter diminishes, then we call this numerical methods asymptotically compatible. So they will be much more robust in the sense that it doesn't matter how you pick your delta and h, where you're making one go to 0 or faster than the other. If you set the delta finite, you're doing the non-local calculation. You're setting delta smaller as you refine your grid size, then basically you're solving your PDEs. You should produce the same result as your standard software coming from elasticity. Right? Or even better yet, if you put your non-local range of parameters equal to 0 in your computational code, you just end up with a discretization of the PDE, if that PDE makes sense. So what kind of numerical methods will preserve this kind of property? Okay. So the study was motivated by the fact that not all the numerical methods people have been using in the community will preserve this nice property. And in fact, some of the popular ones tends to give you convergent numerical methods, but to an incorrect physical solution. So in her first paper that Xiaochuan Tian wrote, he was solving really a 1D, a simple baby model, linear models, and using the simplest type of discretizations. It's an integral model, so you can just do Riemann sum as quadratures. Or if you do it as a versional problem, because your solution may be discontinuous, so you would use the simplest finite element with piecewise constant. Normally, for solving second-order PDEs, you don't use that. You use piecewise linear functions. But here, we could afford to use piecewise constant. So people have been using that. Okay. So she did numerical calculation. So she did the calculation, for example, made her horizon parameter 3 times the mesh size. Okay, so she's increased the number of particles, will refine the mesh size, but at the same time she's making the non-local range of parameters delta smaller. Why does she do that? Because this ratio determines the bandwidth or the sparsity of the linear system she has to solve. So by keeping that constant, she's really solving a matrix with the same bandwidth. So that will not increase the storage. So she did the calculation, though she did another calculation, made the grid finer. Well, the numerical solution falls on top of each other. So it's great. Numerical solution now converged. We don't see any difference. Okay? But turns out that that curve is nowhere close to the actual limit that we should be getting, which was a solution to the elasticity equation that stays way on top of the numerical solution. Okay. So it turns out in this numerical discretization, we're doing something consistent, but we're consistently overestimating the elastic constant. We're underestimating that by a factor of 3. So the numerical the solution, the elastic constant gets smaller, but the solution itself gets amplified by a factor of 3. So, sorry, I called it the other way around. The elastic constant numerically estimated becomes 3 times bigger. Okay, so the numerical solution was a third, if not proportionally correct, of the original one. Okay, if this ratio becomes bigger and bigger, if you take 5 times, then that overestimation will become less dramatic. Okay, so engineers have found this one in their computation. They say that somehow when they're taking wide stencils, when the number of particles get fixed, they can get good numerical methods, but up to, say, for example, 5% error. And then no matter how they refine, that error will no longer diminish anymore. Well, that 5% error is really because of discrepancy in the estimate material constant, numerical constant, and also the model constant, right? So that's not because of the loss of accuracy. It's really because you have incorrect numerical methods. And so if you don't have the right numerical schemes, you will not be able to discover this kind of phenomenon. And if you develop asymptotically compatible schemes, which we have offered tons of remedies to say what kind of methods will be asymptotically compatible, and if you use them in practice, you can make your code much more robust. This is very good for effort of building open source code. Your intention is to let other people download and use them, and if the code is not robust, if you put some parameter, slightly change the ratio, you get different results, and that could be disaster, right? So it's a good lecture. It's a good lesson to learn. Okay. And so that was work motivated by computational experiments and allowed us to generate a lot of work on algorithm development and also a mathematical theory to analyze those methods. Okay. I think I have 50 minutes, right? So I don't want to drag too long. I actually prepared a lot of materials. Let me just maybe spend a couple minutes to say briefly on this. So non-local models, certainly there's no free lunch, right? And it increases the computational complexity. How can you make non-local models compete at some level with local models? One of the possible strategy maybe is to explore the coupling of non-local models with local models, because hopefully singular solutions like cracks don't develop everywhere. They develop in some concentrated regions, and that's where you need astrophysics. And the non-local models preserve or pick up additional physics and allows you to deal with those singular behaviors. But away from singularity, the quantities are smooth. Local approximation is good if you have a way to couple them together, and that could reduce the computation significantly, right? So the issue will be how you can couple them together. And you may have a situation like pictorially depicted like this. I would assume that there's some local region that's given by PDE. I just wrote a simple example. But then there will be a non-local model given by an integral equation. So how do I tie the non-local model with a local model where you think about range of interaction is going to 0? So the strategy we used, as this picture showed, is to use what we call as a heterogeneous localization. So in the singular region, we have singularities. There is a finite range of interaction, so we have a large delta. But as we move away from the singularity, I'm going to put this range of interaction smaller. Actually, at some point, I'm going to decide I'm going to set this delta equal to 0. Then on this side will be completely local. Right? So I don't need to incorporate non-local effect anymore. And this poses a mathematical dilemma in the sense that the tools we develop on this side are all dealing with functions which are not very smooth. But on this side of PDEs, the solutions have reasonable regularities. So how do you put the spaces together to have a seamlessly integrated together problem together? It's going to be a challenge. For example, solutions over this side, functions in the space H1 can have a well-defined trace on the boundary, but the non-local model generally do not share that property. Okay. So you need to develop some mathematical theory to say, if you do this localization, this heterogeneous localization, actually you can pose some nicely boundary value problems using information on a low-dimensional interface. Right? So that needs you to generalize your mathematical theory developed for PDEs. For example, there are results like Harding inequality. There are results like trace theorems. A function in H1 maybe will have a H1 half regularity on the boundary, but we actually can refine the result by using a non-local space ideally suitable for this non-local model with heterogeneous localization. So with this motivation of developing more effective numerical methods, we actually accidentally discover some better mathematical description of the theory, right? So I summarize that as a sentence to say, when you're solving non-local models, or when you're solving a complicated problems involving multiple processes, what would be the effective model? Well, perhaps a non-local model could be an effective option. So you should keep that in mind. Think about doing something non-locally. But if possible, you should try to localize that everywhere you can afford to do that. And this will make your computation more effective. And if you have this asymptotically compatible scheme we developed, then you can use a single discretization. And they are consistent in both the non-local regime and the local regime. They're going to solve your non-local model in the non-local region, and they're going to solve your local model in the local region. And you don't have to develop separate codes, and you can use this one kind of discretization to deal with this transition of different regimes. So that could be an effective numerical strategy. Okay, so this fulfills our really our goal to develop that asymptotically compatible schemes. Okay. There are many other works, but I better cut my lecture short. Let me just give you one last thing. Okay, so this is the latest hobby I got into, is to model self-driving cars. So there's a big community of people working on traffic flow models, not for individual cars, but thinking about you have a density of cars driving on the highway or in a city, and what will be the collective behavior of the car traffic, automobile traffic. So in the old days when you're driving, you just worry about what's the car in front, what's the car in the back. So basically you're making decisions using local traffic information. But now with connected vehicles, you're getting information about how many cars are way ahead of you, or how many cars are at the intersections, they're blocking you. You get GPS data. So you're doing driving decisions much more intelligently. So the traditional traffic flow model, like LWR model, are no longer suitable for this self-driving cars. So we're trying to incorporate non-local features into the modeling behaviors, and there are some progress on this line. I don't have a lot of details to report at this moment, but just to say that if you, in some sense, if you're able to make the choice more intelligently by deciding your local driving speed, but not using the local density, but rather using densities around you, then you can stabilize your flow much more effectively than otherwise. If your typical local LW model, you can get into this kind of stop and go waves. So those like a shock wave for your conservation laws, and you get stuck in the traffic, stop and go, right? But with this non-local models, you can show that those kind of behavior will dissipate because you have a better driving strategy. All right. Well, so there are other applications, but let me cut my lecture here. So we've done a lot of work, but this work largely done with collaborators. I list many of them. I can't really name them one by one. A lot of very brilliant students and postdocs. Xiao Chuntian, I told you, she's going to be at UCSD as a faculty. Tadeli Gensa was my postdoc. He's now a tenured faculty in Tennessee. And then there are many others. So with that, I will conclude. So my last message will be, I hope that when we're doing mathematical models, we can think more about non-local features, and it might be useful. It could be an alternative, could be a bridge, and could be useful to even for discrete models, for local models. Thank you very much.